Welcome back, dear students. This is Ramana sir, physics. How are you all? The second year LAQs, long answer type questions, most important questions for final examination purpose. Very useful by easy method. I am discussing from waves chapter. Waves chapter, there are 6 long answers are there. So in that, first 3 are most important. So in that, the first one is formation of stationary wave in stretched string, and second one is formation of stationary waves in open pipe, and third one is closed pipe. So in that first one, formation of stationary waves, the last question, explain the formation of stationary wave in stretched string, hence deduce the laws of transverse vibrating string. First of all, in this question, so we have to know about what is stationary wave. They are asking formation of stationary wave in stretched string. Stationary wave means what? What is stationary wave? First, we have to know about stationary wave means what. Here, the two transverse waves. Here, first transverse wave you can observe with blue line, and the second transverse wave in opposite direction you can observe with the black line, black wave. Here these two are having same frequencies and amplitudes, but they superimposed in opposite direction. Opposite direction. So this superposition of the two transverse waves are called stationary wave. Here, when two equal frequencies and amplitude waves are moving in same medium, but they superimposed in opposite direction, the two transverse waves superimposed in opposite directions called stationary wave. Here at fixed points, for string purpose we are observing, so consider a string. The string is fixed between the two rigid supports, and the string is just plugged at right angles at the midpoint. What happened? The one transverse wave is traveling and get reflected from the other end. These two transverse waves are superimposed. At fixed points, nodes are forming. Here node, here also node. Here node, 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 node. Wherever displacement is 0 or amplitude is 0, their nodes are formed. And wherever amplitudes are maximum, antinodes are formed. Amplitudes are maximum, antinodes are formed. So like this, node and antinodes are formed alternatively. Nodes and antinodes are formed alternatively. Here the distance between two successive nodes, we can take half of the wavelength. The first wave displacement, the two transverse waves are there. The first transverse wave displacement formula, y1 equal to a sine kx minus omega t. Second wave is superimposing in opposite direction, so that is why the y2, second wave displacement y2 equal to taking a sine kx plus omega t. Why? Because it is coming opposite direction. The two waves are superimposing, then resultant wave. Therefore, the resultant displacement y equal to y1 plus y2. Resultant displacement y equal to what? y1 plus y2. Substitute the values, y equal to a sine kx minus omega t plus a sine kx plus omega t. Here y equal to, here a I am taking common, sine of kx minus omega t plus sine of kx plus omega t. Here y equal to a into, here we know that sine of a plus b plus sine of a minus b formula is 2 sine a. Sine a means what here? Kx, and cos b, 2 sine a cos b. Cos b means what? Cos omega t. Here sine of a plus b plus sine of A minus B formula 2 sine A cos B. So that is why A as it is 2 sine A cos B. Instead of A, kx is there. Instead of B, omega t is there. Here y equal to 2A sine kx cos omega t. 2A sine kx cos omega t. Here the resultant amplitude is what? 2A sine kx. This is called resultant amplitude. I am writing here the resultant amplitude AR is equal to 2A sine kx. Why? Because this is the form of A cos omega t. Y equal to A cos omega t waveform. The resultant amplitude is how much? AR. AR equal to 2A sine kx. Here where kx equal to n pi, if you take kx equal to n pi, if you take n pi, here n values 0, 1, 2 and so on. So that time what happened that time? So 0, if you substitute here instead of n, what happened? Kx is 0. So kx value 0, if you substitute, what happened? Sin 0 value is what? 0 only. 0 into something is what? 0. So therefore AR equal to 0. Wherever amplitude is 0, so is called, so that point is called what? Nodes. Nodes are formed. Wherever amplitudes are 0, so that point is called what? Node. Here nodes are formed at kx equal to n pi. Where kx equal to n plus half into pi. Here also n values 0, 1, 2 and so on. Substitute here n equal to 0, what happened? 1 by 2 into pi, that is pi by 2. Kx is pi by 2 means sin pi by 2 is how much? 1. 1 into 2a, the resultant amplitude is what? AR equal to 2a. Here AR equal to 0 we got. Here AR equal to 2a means maximum. That means that time what happened? Maximum amplitudes are called what? Antinodes. Here antinodes are formed. Here the resultant amplitude is what? Minimum. Here resultant amplitude is what? Maximum. Here minimum and maximum alternatively. That points are called nodes and antinodes. So next we have to discuss the fundamental frequencies or harmonics. Okay, fundamental frequencies and harmonics in stretched string. So now we'll discuss. In this harmonics, first case, fundamental frequency or first harmonic. If the stretched string is vibrated with single segment, so that time fundamental frequency or first harmonic will form. So string is vibrating with single segment. Whenever string is plucked at right angles, what happen? If it vibrates with only single segment, so that time fundamental frequency or first harmonic will form. Here at fixed points, nodes are formed. Just now we derived node and antinodes derivations. And at maximum, this is a forward wave, this is a reverse wave, both the waves are superimposed. Here at maximum displacement, maximum amplitude, the antinodes are formed. Here the distance between node to node, just now we discussed total length of the string is say L. L equal to distance between string is how much? Lambda by 2. L equal to lambda by 2. Lambda equal to what? L equal to lambda by 2 means lambda equal to 2L. So this diagram, so draw as it is and so derive the lambda value, lambda equal to 2L we got. Now transfer wave velocity formula. So in this string, for string transfer wave velocity formula, V equal to under root T by mu. V equal to what? Under root T by mu, where T is tension in the string, tensioning string, and mu is linear density. Mu is called linear density. This is mass per length. Linear density definition is what? Mass per length. Here, but the velocity of this sound wave, we know that from V equal to n lambda formula, from V equal to n lambda formula, n equal to what? V by lambda. V equal to n lambda, n equal to V by lambda. N equal to, substitute the values V value and lambda value. What happens? N equal to V by lambda. V value is how much? Under root T by mu whole divided by lambda value is what? 2L. So therefore, I am writing this one as N1 is equal to 1 by 2L into under root T by mu. 1 by 2L into under root T by mu. This frequency is called fundamental frequency or first harmonic. So we have to write, therefore this frequency is called fundamental frequency or first harmonic. This is the fundamental frequency or first harmonic, the derivation. Okay, so next we will see second harmonic or first overtone. This one, second harmonic or first overtone. Here harmonics will form continuously. The possible frequencies are called what? Harmonics. The higher than the harmonics are called overtones. Here second harmonic means here first overtone is forming. Here in the second harmonic or first overtone, the string vibrate with two segments. Here two segments are forming in this, you can observe. Here the first, at fixed points we know that nodes are formed. Wherever amplitudes are zero, also nodes only will form. Wherever amplitudes are maximum, antinodes are formed. Here we know that the node to node distance is how much? Lambda by 2, half of the wavelength. Here another segment is there. Here also half of the wavelength, lambda by 2. Here lambda by 2 and lambda by 2. Total length of the string L equal to, we can take lambda by 2 plus lambda by 2. Total how much? L equal to 2 lambda by 2. Here 2 gets cancelled. L equal to lambda. L equal to how much we got? Lambda. Now same like that only from transfer wave velocity formula. V equal to what? Under root T by mu. Here where T is tension in the string, mu is linear density, already we taken. From V equal to n lambda. From formula velocity of sound, V equal to n lambda. N equal to what? V by lambda. N equal to V by lambda. Substitute the values. V value how much? Under root T by mu. And lambda value is how much? L. Here what I am doing, with 2 I am multiplying in this equation, and this L I am writing outside. With 2 I am dividing. With 2 multiplying and with 2 I am dividing into under root T by mu as it is. T by mu is as it is. We know that in the last class, fundamental frequency formula, how much we got? 1 by 2L into under root of T by mu. That meaning, therefore, this second harmonic, that is why N2 I am taking. N2 equal to 2. This value is how much? 1 by 2L into under root of T by mu. Value is how much? N1. Therefore, N2 equal to how much? 2N1. This frequency is called second harmonic or first overtone. Second harmonic or first overtone. So now we'll see last case, third harmonic or second overtone. The last case we can observe third harmonic or second overtone. If the string is vibrating in 3 segments, so that time third harmonic or second overtone will form. So we know that the node to node distance is lambda by 2. Here also another segment lambda by 2. The last one lambda by 2. Total length of the string L equal to lambda by 2 plus lambda by 2 plus lambda by 2. Total is how much? L equal to 3 lambda by 2. Lambda equal to what? 2 into L, 2L divided by 3. Lambda value how much we got? 2L by 3. We know that transfer wave velocity equation v equal to under root of t by mu from v equal to n lambda formula. N equal to what? V by lambda. Substitute the values. V is what? Under root t by mu. And lambda is what? Just now we got 2L by 3. So this 3 is sent to numerator. What happens that time? N equal to 3 into 1 by 2L. This 3 is in denominator. Again in denominator we can send to numerator. 1 by 2L into under root t by mu. Therefore N3 equal to what? 3N1. N3 equal to 3N1. This frequency is called harmonic or second overturn. The last the ratios of harmonics N1 is to N2 is to N3 is how much? Here the N1 is to N2 is to N3 equal to 1 is to 2 is to 3. Why? Because here N1 value we got 1 by 2L into under root of t by mu. N2 value we got N2 equal to 2N1 and N3 value we got 3N1. So therefore the ratio of harmonics how much we got? N1 is to N2 is to N3 equal to 1 is to 2 is to 3. Continuation the loss of transverse vibrating string. Now we'll discuss the loss of transverse vibrating string also. Laws of transverse vibration. There are three laws are there. First law or law of length, second law or law of tension, and third law or law of linear density. We know that when the string is vibrating with fundamental mode, what is the formula? N equal to 1 by 2L into under root t by mu. Here first L, the fundamental frequency, okay, is inversely proportional to the length. So that is first law. Here second law means fundamental frequency directly proportional to the square root of tension. There L and mu are keeping constant. Next third law time fundamental frequency is inversely proportional to the linear square root of linear density, where length and tensions are keeping constant. Here the fundamental frequency when the string is vibrating in fundamental mode, so that time the fundamental frequency N is direct inversely proportional to the fundamental frequency is inversely proportional to the length. So that meaning is what? Tension and linear densities are keeping constant. T and mu are keeping constant. Keeping constant. Here N is inversely proportional to length, or N is N L bring this side, NL is equal to constant. This is called first law or law of length. Second law means when the string is vibrating in fundamental mode, so that time fundamental frequency is directly proportional to the square root of tension, where length and linear densities are keeping constant. N is inversely proportional to square root of tension. N by root t equal to constant also we can write. The last law, linear density, law of linear density or third law. In this fundamental frequency of a stretched string is inversely proportional to the square root of linear density. Here we can write N, or we can write N root mu equal to constant also we can write, where length and tensions are keeping constant. Length and tensions are keeping constant. Till here you have to write, so you will get the 8 marks. Sometimes attachment problem also they'll ask. Okay, that problems, which type of problems they can ask. So that also I'll discuss in this class continuation. Don't skip the video. If you understand problem, if you write the problem, so then only you will get the 8 by 8 marks. First question you can check on screen. A stretched wire of length 0.6 meters is observed to vibrate with a frequency of 30 Hz in the fundamental mode. If the string has a linear mass of 0.05 kilogram per meter, find first bit the velocity of propagation of transverse wave in string, second bit the tension in the string. Here in this question given data, The length of the string is given 0.6 meters and the fundamental frequency, the string is vibrating in fundamental mode. So the time fundamental frequency N1 value is given 30 Hz and the linear mass means nothing but linear density mu value is given 0.05 kilogram per meter. Two bits they are asking. One is velocity of sound, how much in the string, and T is tension in the string is how much. First, the velocity of transfer wave will find. Okay, so here from fundamental frequency for string, fundamental frequency formula N equal to V by 2L. Here V value under root of T by mu. I am not substituting. Why? Because V only we have to calculate V by 2L. V equal to what? N1 into 2L. Substitute the values. V equal to N1 fundamental frequency is given. How much given? 30 Hz into 2 into L. L is how much? 0.6. Solve this one. V equal to 30 into 2 into 0.6, that is 1.2. 1.2. So here 0 and decimal cancel. 12 3s are how much? Therefore 12 3s are 36 meter per second. Velocity of transfer wave we got V equal to 36 meter per second. Next we will find the tension in the string. B bit will find. Okay, B bit is what? Tension in the string. So T is how much they are asking, tension in the string. From transfer wave velocity formula we know that V equal to what? Under root of T by mu. Why? Because here linear mass, that is nothing but linear density also given. Here squaring on both the sides, V square equal to, and here square root gets cancelled, T by mu. T we have to calculate, take as subject T equal to V square into mu. Substitute the values. T equal to V square. V how much we got? Just now we got 36. 36 whole square into mu value. Linear density how much? 0.05. Here T equal to 36 whole square. 36 into 36 into 0.05. Solve this one. You'll get T. Next question you can take. A string has a length of 0.4 meters and a mass of 0.16 grams. If the tension in the string is 70 newtons, what are the three lowest frequencies it produces when plucked? Question. The length of the string is given 0.4 meters and the mass of the string is given in grams, given 0.16 grams. Here the convert to kilograms, how much? 1 gram converting into kilograms, how much? Into 10 to the power of minus 3 kilograms we have to write. And tension in the string T is how much? 70 newtons. And what they are asking? First to three lowest frequencies N1, N2, N3, how much they are asking. So first we will find the fundamental frequency. N1 value will find. So from fundamental frequency formula, fundamental frequency N1 is equal to 1 by 2L into under root T by mu. What is the formula? 1 by 2L into under root of T by mu. Substitute the values. N1 is equal to 1 by 2 into L is how much? 0.4 and under root tension is 70 by linear density. Here linear density means what? Mass per length. Mass per length. Linear density is what? Mass per length. Here mass is how much? 0.16 into 10 to the power of minus 3 by length. Length is how much? 0.4. Okay. So here this 0.4 N1 is equal to 1 by 2 into 0.4 is how much? 0.8. And this 0.4 sent to numerator, 0.4 by 0.16 into 10 to the power of minus 3. So after solving, so you will get this one, 523 Hertz will get. N1 value how much? 523 Hertz you will get. The first fundamental frequency we got 523. So next what they are asking? Second harmonic they are asking. First three lowest frequencies. First one we got. Second one N2 we have to find. N2 is nothing but what? Second harmonic is twice of the fundamental frequency, that is 2N1. N2 equal to 2 into 523. N2 equal to 2 into 523, that is N2 equal to how much? So 1046 hertz. This is the second lowest frequency. The last one N3. N3 equal to what? 3N1. So that is N3 equal to 3 into 523. Here N3 equal to, multiply here, 3 3s are 9, 3 2s are 6 and 3 5s are 15. 1569 hertz. Therefore, first three lowest frequencies are 523 hertz and 1046 hertz and 1569 hertz. So this is the answer. And the last one, you can take a string mass 2.50 kilograms is under a tension of 200 newtons. The length of stretched string is 20.0 meters. If the transverse jerk it does cause at one end of the string, the how long the disturbance take to reach the other end? In this question, the given data, if you observe, the mass of the string is given 2.50 kilograms and the tension in the string is given 200 newtons and the length of the string is 20.0 meters. What they are asking, so how long, so how much time it will take to jerk from other end, they are asking. Here from, to find the t value, first we have to find the velocity v value, we have to find. The transfer wave velocity v equal to, what is the formula? T by mu, but mu is not given. So what to take? Mass per length, m by l we have to take, m by l. So that equal to what? Under root TL by m. So this L I am sending to numerator. Substitute the values v equal to under root. T is how much? 200 and L is how much? 20.0, that is nothing but 20, and m mass is how much? The mass is 2.50 kilograms. So solve this one, so you'll get, okay, 40 meter per second you'll get. Solve this one, you'll get 40 meter per second. How long they're asking? T equal to velocity equal to displacement by time. Time equal to what? Velocity equal to displacement by time. Time equal to what? Displacement by velocity. Displacement is nothing but what? Length. 20.0 is there. 20 I am taking by 40. 21 ja 22 ja 1 by 2. That is 1 by 2 means how much? 0.5 seconds. How much time it will take? 0.5 seconds. So these are the waves. Okay, first LAQ, most important LAQ, the formation of stationary wave in stretched string. The continuation, open pipe, closed pipe, also there in the next part. Okay, the video become very lengthy, so that is why I'm stopping now. Okay, so here next class I'll discuss the open pipe, closed pipe along with the numericals. Okay, so I have given in description the open pipe and length pipe. Okay, so please watch that open pipe, closed pipe case also. Compulsory question in AP and TS final examination, IP second year final examination, compulsory questions. Okay, so thank you for watching. Thank you.